Hello everyone and welcome back to Nunley Math. I'm your host Aaron Nunley. I want to thank you so much for joining me here today as we begin a discussion of monomials and monomial operations with a focus on multiplication and division. This is sort of a transitional lesson for us where we are going to move away from talking about exponent and exponent rules proper and begin talking about how we use those to work with monomials and polynomials. Now certainly when I say that, that does beg a particular question, and that is this: what is exactly a monomial? So I thought I'd take a moment and talk about that word for just a second. It is constructed of the prefix mono and the suffix nomial. Mono and nomial, when they're combined, form the word monomial. Mono is a prefix that we use when we're referring to one of something, and nomial is a suffix that has actually multiple meanings that are all closely related to one another. It can mean a number, a name, or a term. So when we talk about monomials in an Algebra 1 class, what we're talking about is an algebraic expression that acts as a single term, and that's going to come up quite a bit over the next several days, a single term. We can actually take monomials and connect them together to create polynomials, and of course the prefix poly means many numbers or many terms. A monomial can be one of three things. It can be a constant, it can be a variable, or it can be a product of constants and several variables. Now I know that is not necessarily terribly helpful for some of us, so let me give you some examples of what that might be. The number 5 is a type of monomial because 5 is a number or a constant. It's something whose value does not change, it's always the same. Likewise, 8 is a constant, negative 10 is a constant, and 3/5 is a constant. So any number written by itself is, in fact, a monomial. A is also a monomial because it meets the definition of a variable. It is simply a number you do not know. B would be a monomial, M would be a monomial, and X would be a monomial. What's of more interest or greater interest to us is this last idea here, this product of constants and several variables. Product, of course, means multiplication. So if I were to give you 3 times x or 3x, that is considered to be a monomial. 4xy is a monomial because it is the constant 4 multiplied by an x and multiplied by a y. Negative 7x cubed is a monomial because it's a negative 7 times an x times an x times an x. And 15x squared y squared is also a monomial because you have the constant 15 multiplied by an x times a y, which is of course just several variables. Notice that all of these things are often treated as a single value or a single number. That's the reason why when I say 3 times x, I don't always write the times sign in between. In fact, it's customary not to, because when I put those together, they have certain behaviors that are the same as the behaviors you might have with a 5 or an A or an 8 or a B. They act in a certain way, and so we write them together so that we can recognize that they act as a group in a particular way. Now I do want to make sure I point out a couple things that are not monomials, just so you have something to compare this to. 5 plus x is not a monomial because a monomial must be a constant, a variable, or a product of those. This is not a product. This is actually a sum because it's using addition, not multiplication. We would actually say that this is the sum of 2 monomials. You have the monomial 5 and you have the monomial x, but you put them together, it is no longer a monomial. 8x to the negative second is also not a monomial because even though it looks like you have an 8 multiplied by a bunch of x's, we have to keep in mind that this negative exponent tells us to use the reciprocal. This is actually division, not multiplication. Remember, x to the negative 2 is the same as 1 over x squared, and 8 times 1 over x squared is 8 over x squared. It is division. Now, I personally think this is a very fine distinction because you can take any division problem and rewrite it into a multiplication problem by using its multiplicative inverse. But when we're defining monomials, it's very it's very important that you recognize this is not classified or considered to be one. So let's talk about multiplying monomials. When we multiply monomials together, we're going to use the commutative and associative properties along with our exponent rules. So that if I were to give you something like 5x times 3x, this problem actually might look familiar to you because it does resemble some of the problems we used when we were learning our exponent rules. In particular, the what's that, product of powers property. So just be aware that I am aware this is something you might have seen before, and you can probably work that out using a different method than what I'm about to show you, but I do want to walk through the process to show how we can do this using commutative and associative. Remember, if I have 5x times 3x, this is a monomial times another monomial. We need to realize that monomials are products, meaning this is 5 times x multiplied by 3 times x. In fact, since there's a multiplication in between here as well, this is actually one long string of multiplication. Now you'll notice I've removed the parentheses because if it is one long string of multiplication, the associative property of multiplication says it doesn't matter how I group my numbers. If a group of things are multiplied, you can reorganize them in any way you want. So that's what I've done here. In addition to that, the commutative property says it does not matter what order we list our numbers in if everything is multiplication. I could do the 5 times 3 first, I could do the 5 times 3 less. I can rearrange and reorganize these any way I want to in order to make it easier to multiply. Now in this case, it's extremely helpful to reorganize those because now I can do the 5 times 3 and get my 15, and I can do my x times x and get 15x squared. Notice I regrouped those so my like things were together because I know I can multiply these and I know I can multiply these, and I get 15x squared. Notice this is the associative property, which says I can ungroup them. The commutative property says I can rearrange them, and the associative property says I can regroup them again. Let's try another one. It's a little more complicated. 7x squared y times negative 2xy. This is a monomial, the product of constants and variables, times a monomial, the product of constants and variables. Once again, I can take those numbers and I can get rid of the parentheses because it's all one long string of multiplication anyway. That's the associative property. Since it's one long string of multiplication, I can rearrange it any way I like. That's the commutative property. It looks like I have a random z that popped in there. That must have been a keystroke error. I'll get rid of that later. And then I regroup it once again using the associative property. Notice I did correct that z error, so just pretend that's not there. And then once I regroup it, I can use my exponent rules to say 7 times negative 2 is negative 14, but this is x to the third and y to the second. Negative 14x to the third, y to the second. Check out another example. You might want to pause the video and try this on your own. It is the exact same thing, it's just a little bit longer. I'm going to assume you've already done that, and I'm going to keep going. The associative property says I don't need those parentheses because it's just one long string of multiplication. The commutative property says the order doesn't matter when you multiply, I can rearrange it any way I want. The associative property allows me to regroup the like things together, and then I just use my exponent rules to come up with 8, a to the fifth, b to the third, c to the second. It looks as though I've dropped a negative sign right there, so we'll go back and we'll just write that in by hand. How's that? A little better? Okay, negative 8, a to the fifth, b to the third, c squared. Now, when you look at this, you're probably thinking, this seems to be an awful lot of work. It would be nice if I could go from here all the way down to here and skip all this messy stuff in the middle. And in reality, most mathematicians, most people are not going to bother doing all of this. I do all of this to help you understand why, when I start taking these numbers, it's okay for me to combine the things that I do. I'm going to do the next set just by jumping straight from here to here and talking through this stuff in our mind, along with using my exponent rules. Check this out. 11x squared times 9x. Here's what I realize when I look at this. I realize when I rearrange and regroup, eventually this 11 times 9 is going to make a 99. I also know when I rearrange and regroup, I'm going to end up taking my x and my x and my x, my 3 x's, and multiplying those together. So rather than taking the time to write all that out, I'm going to say 11 times 9 is 99, and x squared times x, my product of powers property, says I can take those 2 and those 1, add them together and get 3, and this becomes 99x to the third. I'm going to use the same shortcut here. I know that 12 times 7 makes 84. I also know that once I rearrange and regroup, I'm eventually going to have those 3 x's and these 2 x's grouped together, giving me 5 x's. And I know I have 1 y here and 1 y here for a total of 2 y's. Any idea what that's going to equal? 84 x to the 5th y squared. Why don't you pause the video and try this one on your own real quick, and then I'll come back and show you what I've got. I'm going to assume you've done that. Negative 8 times negative 13 is going to make, let me underline that, 104. I can see that I'm going to have 6 a's multiplied together, and I'm going to have 4 a's multiplied together. That's a total of 10. 7 b's and 3 b's is a total of 10. And then 4 c's and 1 extra c is a total of 5, giving me 104, a to the 10th, b to the 10th, c to the 5th. Remember, a lot of times our exponent rules are developed by an understanding of commutative and associative properties, and then just taking some shortcuts and some liberties with that. As long as we have a justification for why we're doing the changes, we know we'll be okay. Here's another set. If I divide monomials, I'm going to do something very similar, but this time I'm going to use my fraction rules and the identity property, and as well as my exponent rules to divide the monomials. Check this out. If I have 3m to the 6th n to the 4 over 12m to the 4th n to the 3rd, I'm actually going to take this and split it so that each type of number is together. My type of number, that's a very informal, probably inappropriate way of saying, I'm going to look at the 3/12, my constants. I'm going to look at my m's, and then I'm going to look at my n's. I know I can split this way because when we talk about the multiplication rules for fractions, if you want to find the answer to a multiplication problem and you have a fraction times a fraction times a fraction, the rule is multiply the numerators together, which I did, and multiply the denominators together, which I did. There again, the focus today is not necessarily on fraction rules, but just realize that since this is all one long string of multiplication, I can split this into a product any way I like. Once I've done that, I'm going to go through here and simplify each of these pieces independently. For example, 3/12 I know is going to simplify to 1/4. If I have m to the 6th over m to the 4th, I know that can simplify. Now, we learned in a different lesson that if I have m to the 6th over m to the 4th, that is the quotient of powers property, which says all I have to do is subtract those exponents, which gives me m squared. And the same thing is done here on this last one. N to the 4th over n to the 3rd, the quotient or the quotient of powers property says I can subtract those, and that makes this n to the 1st. Notice I don't write the 1 on n to the 1st. Once I've simplified those, I just multiply my numerators together. 1 times m squared times n, 4, and then I do the same thing with my denominators. 4 times 1 times 1, giving me m squared n over 4. And that's not too bad, right? Try this one. 22 m to the 9th n to the 4th over 55 m squared n to the 7th. Just like before, I'm going to split this into 3 fractions, where the things that are alike are together. And then I'm going to deal with those fractions one at a time. I'm going to take 22 over 55, and I'm going to realize both of those have an 11 inside of them. I get rid of the 11 they have in common using my identity property. I then look at my m's. M to the 9th over m to the 2nd leaves me with m to the 7th, and anything that's not a fraction is always over 1. And then I have n to the 4th over n to the 7th, which is n to the negative 3. Now, I am not going to leave this as n to the negative 3rd. I'm actually going to write it in simplest form. Remember, a negative exponent says use the reciprocal. So this is 1 over n to the 3rd. If what I did here was confusing to you, you may want to go back and rewatch the video on zero and negative exponent rules. Once this is simplified, I multiply my numerators together, I multiply my denominators together, and I get this. I've got one more for you. I would challenge you to try this one on your own by pausing the video and then restarting it to see how I do this. I am going to go ahead and keep going, assuming you've already done that. 27 over 63, a to the 6 over a to the 3rd, b to the negative 4 over b to the negative 9. Once again, I'm going to deal with these one at a time. 27 over 63. I can look at both of these and see that they both have a 9 hiding in them, so I'm going to use my identity property to get rid of that 9. A to the 6 over a to the 3rd, I subtract those, that's a to the 3rd. B to the negative 4th over b to the negative 9 is often a trouble spot for people. Remember, the quotient of powers property says we subtract those. When I subtract negative 4 minus negative 9, I get b to the 5th. When I put this back together, I get 3a to the 3rd, b to the 5th over 7. Now, this is the long drawn out way of doing this. This is the proper way to demonstrate so that we understand what's going on. But most people are not going to take the time to do that entirely the way I've shown you. I wanted you to understand it because we're going to use the same logic on a problem like this, but we're not going to show all those steps. Instead, I'm going to look at this problem right here, and I'm going to say, okay, let's look at the 14 over 49. You remember before I was writing that out by itself. I'm not actually going to do that this time. I'm just going to look at 14 over 49, and I'm going to realize that when I simplify this, both of those can be divided by a 7, and it's going to turn into 2 7s. I'm then going to look at my c to the 11 over c to the 5, and I'm going to say, oh, well, there's 11 c's on top, 5 on bottom. When I simplify, what's going to happen is these are going to go away, and I'm going to be left with 6 on top. I did that by talking about simplifying fractions. You could also do it using the quotient of powers property, which says that we just subtract the exponents. And then I'm going to look at this one right here, and I'm going to realize I have 8 d's on top and 10 d's on bottom. So when I simplify it, or if I use my exponent rules, I'm going to get 8 minus 10, which is negative 2. Remember, negative 2 is a negative exponent, and we do not leave negative exponents in our answer. That means that negative 2 is going to send the 2 to the bottom. This is going to become d to the 2nd. So when I put all that together, I end up with 2c to the 6 over 7d to the 2nd. Easy enough, right? Try this one on your own real fast. I'm going to go ahead and work it out, assuming you've done that. Negative 15 over 40. Both of those can be divided by 5. This is going to be negative 3 on top and 8 on bottom. When I look at my s's, 6 minus 4 means I'm going to be left with 2. And 4 minus 4 is going to leave me with t to the 0. Anything to the 0 power is a 1, which means this is going to go away completely, leaving you with negative 3s squared on top and just the 8 by itself on bottom. Let's do one more of these. Here again, I would suggest trying this on your own before watching the video, but I'm going to keep going here. 42 over 54. Both of those have a 6 hiding in them. So this is going to simplify to 7/9. When I look at my g's, I have 2 on top and 7 on bottom. 2 minus 7 is negative 5, meaning I'm going to have 5 left on the bottom. Remember, negative 5 says use the reciprocal or send those 5 to the bottom. H to the negative 4 over h to the 3. Negative 4 minus 3 makes negative 7. Since it's to the negative 7, I know the 7 are going to get switched down to the bottom. And of course, notice you have this I out here by itself. So you're going to end up with 7I on top and 9G to the 5th, H to the 7 on the bottom. Hopefully that made sense to you. If not, you may want to watch it again. As always, I do want you to understand what we've done up here in examples 1, 2, and 3, because this logic guides us as we take the same shortcuts down here in 4, 5, and 6. If you ever find yourself stuck on an example like 4, 5, and 6 and you forget a rule, you can always go back and deconstruct and recreate your own rule by going through the long expanded form process. As always, thank you so much for taking the time to watch. Make sure you leave us a comment in the comment section. Make sure you like and subscribe and turn on those notifications so that you won't miss any of the upcoming lessons for Nunley Math Algebra 1. Thank you so much for taking the time to watch. Best wishes to all of you guys. Take care. Bye-bye.